Hello, in this video we're going to be talking about two major topics, continuity and differentiability. How do they mix? Are they friends? What's up? So continuity is saying, hey, the limit has to match up with what our function is doing. And our differentiability is checking still limits, but now in terms of slopes. So there are three conditions that can possibly happen. A function could be neither differentiable nor continuous. So here I've got a jump discontinuity. Also, our slope here is increasing to some value, kind of like 1, and it is constant on the other side. So this is neither differentiable nor continuous. We can be continuous, but not differentiable. So here, as we move along, we have a good limit that we're heading towards. It's 2, and the function does go towards 2 at that point. However, this is not differentiable. As we move towards this value of 2, the slope is like 1-ish, and as we come in from this side, our slope is like 0. So this point is not differentiable because these two limits on either side do not match up. Now then there's the golden example where we are continuous and differentiable. Now I actually did make this actually a linear function. It's not continuing the quadratic. So it is possible to jump off of a quadratic into a linear, but it just matters that the slope coming in here is matching the slope as we come in on this direction. If those two slopes are the same, then we're differentiable. We're having a great time. So in this example, we've got a nice continuous function all the way along here. Everything's fine. We are always heading towards where our limit goes and ends up. Very continuous function. But if we take a look at its derivative, that is not necessarily true. On this piece right here, we get a slope of, let's see, that is up 2 over 4. So we have a slope of 2. So in that area, we have our derivative looks like this. So it's this horizontal function. And then when we move into the next part, we have a slope of -4. So this piece right here, we end up with a slope of -4. So then our derivative is suddenly way down here. You can see that we have a point of non-differentiability because the derivatives are not matching up on either side. The slopes on either side are not the same. So we are not differentiable at x equals 0. And then you can kind of see the other points where we're also not differentiable. We're also not going to be differentiable at 1 because we're going from that slope of -4, and now this thing has a slope of 0. So if we graphed the derivative, it would be right there. That is not matching up with that red line down there. So we are not differentiable at 1 neither. Finally, we can look at our last little piece here. We've got a slope of, let's see, we're going up 4 over 2. So that is 2. Oh, did I get, oh, that one was like a half. It was still, it's wrong, but I'm still right. It's still not differentiable. This is a half. There, I fixed it. That has got a slope of 2. That is all the way up here like a weirdo. That is not matching up with that orange line. The slopes on either side of 4 are not the same. So f is not differentiable at x equals 4. So while it is a totally continuous function, there are 3 points where we are not differentiable. In another video, we talked about types of discontinuities, jump, point, and infinite. There are 4 types of non-differentiability, similar to where we aren't continuous, where we're not differentiable. Any of the points of discontinuity are also points where we are not differentiable. Also, we are not able to be differentiable if we are corner/cusp. Those are basically the same thing. And we are also not differentiable when there is a vertical tangent line. Let's take a look at those. In this first example, I've got this function f of x, and I'm factored the denominator in order to figure out, okay, well, where is it not continuous? That's the first thing I want to check in terms of non-differentiability. Well, we've got infinite discontinuities here and here, where x equals -2 and x equals 2. Infinite discontinuities is a type of discontinuity, therefore, it is also not differentiable there. So if we are differentiable, fun fact, add this to your notes, that if we are differentiable, we are definitely continuous. And we can use that to our advantage to say, hey, if we're not continuous, then we're definitely not going to be differentiable. So this function is differentiable from negative infinity to negative 2. Got to skip over that negative 2, as well as 2. That's how we could write it in interval notation. You could write it in other notations too. That's fine. In this example, we are looking at a corner point. So absolute values are a great place that make corner points, something that's very, very sharp. If it's sharp, we're not able to be differentiable. So right here, it has a slope heading, it's a negative slope, and suddenly shifts to a positive slope. It doesn't have a nice, easy transition from one to the other, from that negative to that positive slope. So it is not differentiable right here at 5. So we are differentiable everywhere to 5. We have to skip over 5, and then we continue forward. You could also write that as an inequality if you prefer. Taking a look at this graph, it is very similar to a corner point. It is basically the same thing. They're never going to ask you the difference between those two, so don't worry about that. A cusp is basically just a corner. So it's another case where we have suddenly a negative slope that shifts very quickly to a positive slope. But it's just a little bit more curvy than that absolute value graph. It's a little curving in there instead of being stuck at that same slope. So right here, we are differentiable from negative infinity to 0 and 0 to infinity. If I think about what's going on with this one, what sort of discontinuity it is, I know it's a cusp, but to show you why, this is basically an absolute value graph. We could graph it on our graphing calculator, but what if this is a non-calculator problem? It is that, but this negative piece has become positive, so it's shifted to do our sweet flying V thing. So this is a cusp discontinuity, if I can spell cusp. I typed it because my penmanship is so bad. Finney's being weird and making you talk about the difference between a corner and cusp, but whatever, I don't really care about it. Just it's sharp, it's not differentiable. That's all we care about. In this example, we have just a regular old cubed root. So cubed root graphs look like this, if I could draw, where they come flat and they go vertical for just an instant. They're not vertical that long. So if we go vertical, then our tangent line is vertical. And if you get that vertical tangent line, that is considered not differentiable because the function stops kind of working at this point because we can't have vertical lines to have a good function, fails the vertical line test type stuff. Cubed root doesn't do that, but the derivative will kind of like blow up and not quite know how to deal with that vertical tangent line because it doesn't know which way to slide after it. So this is a vertical tangent line. Vertical tangent lines are points of non-differentiability, just like a discontinuity would be a point of non-differentiability. In this example, we can see we're dealing with a weird fraction, but that's basically a cubed root graph. So this is the same thing as asking about the cubed root of x plus 4 being squared. So when that thing ends up spitting out 0, it is going to be similar to what's going on up there. So at negative 4 is where we're not going to be able to be differentiable. So this thing is differentiable from negative infinity to negative 4. Scoop, negative 4 to infinity. My slide is a little bit misleading. I actually pulled up a graph for it to kind of see that squaring, similar to the absolute value, is turning the negative part of our normal cubed root graph that should be chilling down here into a positive thing. So this is a cusp point that causes that different non-differentiability. Not a big deal about which one's which, but we do know that we are definitely not differentiable at that negative 4. In this example, what we're going to do is we're going to actually use our proper version of differentiability to show why it is not differentiable at those points. We can kind of like look at our graphs and kind of get an idea of what's going on with slope, but can we actually like analytically show what's going on here? So we need to check what's going on from the left and the right and what's going on with our slopes. So here I'm doing this formula up here, but I'm going to check as x is approaching 1 from the left. So first thing I do, since we're approaching from the left, I want the smaller values. So I get x minus 1 cubed, and then f of 1, which is 1 minus 1 cubed over x minus 1. Then I just simplify this stuff down. That 1 minus 1, that's just 0, so I have this. Then we can cancel one of our x minus 1s, and we've got this limit as x is approaching 1, and then we can just directly substitute our 1, so we get 0. As we do the same thing from the right, we again use the bottom part, not again, but now we're going to use the bottom part because we want the numbers that are going to be bigger than 1. So we plug in it to the bottom stuff. So this x minus 1 squared, and then 1 minus 1 squared, x minus 1. Then we kind of take a look, okay, well, 1 minus 1, well, that's just 0. And so we have x minus 1 squared over x minus 1. We can cancel again. So now we only have this x minus 1, and we get 0. Since those two slopes, not the limits of the function, since the slopes limits are equaling, we can say that this thing is going to be definitely differentiable at that point, since the two derivatives on the left versus right are equal. In this example, we want to use our definition of left and right derivatives in order to figure out, are we differentiable at this point? We don't want to care about the regular limits. We care about what's going on with the limit of our slopes as we're approaching that point. So if we start from the left, we need the values that are less than 2 so we can see what's going on this piece of our piecewise function. So I plug that into that top stuff. So f of x is x plus 1. And then we plug our 2 into this top stuff. This top thing is going to be 5, and we keep x minus 2 in the denominator. As we simplify that down, we get 4 in our numerator, and then we say, oh, well, what can we do to simplify that? Ooh, I could factor that numerator. If I factor the numerator, these x minus 2's are going to cancel each other, and then we're left with this limit as x is approaching 2 from the left of x plus 2, and we end up with a 4. Okay, so that's the left. What is the limit of our slopes as we come in from the right? Well, to come in from the right, we want the values that are bigger than 2. So we use this bottom piece of 4x minus 3, and then we plug in our 2 again. And this ends up being 5. So simplifying that numerator, we get 4x minus 8. And then we say, oh, well, what can we do? Oh, we can factor the 4 out. And once we factor the 4 out, these cancel each other, the x minus 2 and the x minus 2. And so we get the limit as x is approaching 2 from the right of 4. Well, the limit of a constant is going to be a constant, so that's 4. This is 4, that is 4. Our limits are matching up, so boom. Yes, f of x is differentiable at x equals 2, since the left and the right-hand derivatives are equal to each other. 4. In this example, we're trying to figure out, hey, using our left and right-hand derivative, can we be differentiable at this point? So we check left and we check right. So starting from the left, we've got this absolute value thingy. So we kind of put in our 1 and we think about what's going to happen as we use values that are less than 1. So x minus 1, we get 1 minus 1. So, well, that's just going to be 0. Absolute value of 0 is 0. Now I'm going to say that this is negative 1. And where am I getting that? Well, if you think about numbers that are less than 1, so let's go crazy negative, big like negative 30. Negative 30 minus 1, that'll be negative. Negative 30 minus 1, that'll also be negative, but will become absolute value. But these numbers will be the same. So we'll have a negative divided by a positive, or the other way around, and that's a negative 1. So our slope, as we come in on this side, is negative 1. As we come in from the right, same deal. It's going to be that same setup. But now when we think about what's going to be happening, if we use numbers that are bigger than 1, say 40, 40 minus 1, that's going to be 39, absolute value positive 39. 40 minus 1, again, that's 39. 39 divided by 39, that is 1. So our slope is 1 as we're coming in towards 1 on the right. Notice that I didn't use 1. I want to be close to 1. I want to just see what's happening as we approach. But then, hey, wait a minute. The derivative on the left hand is not equal to the derivative on the right hand. No, no, no. Guess what? We are not differentiable at that point. We are continuous. That limit, it's all heading towards 0, and that's where it ends up. But we are not differentiable there. That is a corner point, so we are not differentiable. And the left and right hand derivatives are not equaling. So ends our video about continuity versus differentiability. Continuity cares about where's the function heading and where does it end up. Differentiability cares about what is our slopes heading towards and are those slopes matching up on either side. There are 3 major types really of types of non-differentiability where we can't find the derivative. If we're ever not continuous, then it is not differentiable. Also, if it's differentiable, it is definitely continuous. Corner and cusp points are basically the same thing. And then those vertical tangent lines are, while we are continuous there, we are not differentiable. Thanks for watching. Goodbye.